Good day. In this lecture, we go to chapter 4, data input and output, or data I/O for short. For single character I/O, we can use the getChar function to capture a character constant from the keyboard, and we can use the putChar function to display a character constant on the screen. This is shown in this example. So we can program this. Open the DevC editor. Let's say it's a new file. So you can file new source file, or simply Control N. So we have a new file. Include stdio.h main let's say the character variable is going to be x, so char x. So we use getChar to capture a character constant from the keyboard and assign it to x. Next, we display the content of x, which is a character constant, display on the screen. PutChar the content of x. Hit this compile and run icon. This window will appear. It's a new file. So let's say you can save it anywhere in a pen drive folder. Here I save at the desktop. In this box, the file must have a name. I just name it, let's say ABC. This is important. The extension is .c, not CPP. CPP is C++. It's just C. The box below, select all files, save. So it's going to compile and run the program. The cursor is now blinking. This is getChar. It's waiting for a character constant from the keyboard. Let's say I enter 3 character constant. It will only capture the first one, a single character constant, which is going to be A. That's why we display putChar displays A. You can run again. I enter 8. That 8 is not integer, it's a character constant 8. Enter. PutChar displays on the screen the character constant 8. Next, the string I/O using getS and putS. GetS captures a string constant from the keyboard. PutS displays a string constant on the screen, as shown in this example. Go back to the editor. I'm deleting this. I'm using the same file, abc.c. So let's say we have character array M. So char M. Let's say it can store a maximum of 20 characters. Do not worry. If you input more than 20 characters, the compiler will still accept all the characters. The function getS will capture the string constant entered from the keyboard and store the string constant captured from the keyboard in character array M. Next, we use the function put s to display the content of character array m, display on the screen. If I compile and run, it will replace the old file with the new source code. So this is cursor is blinking, get s, get string constant from the keyboard. We say the size is 20, you can enter more than 20, there's no problem. So put s basically displays on the screen the content of character array m, which is exactly as we entered from the keyboard. Of course, the string constant in this case may contain white space or blank. For example, just now between UTM and Skudai, we have a blank space. The more generic and more often used I/O functions are for input and output are the scanf and printf function. So the scanf and printf functions can be used to capture and display all types of data, integer, floating point, character, or string constant. To enter data from the keyboard, the function is scanf. We have arguments on the right. The control string is basically the formatting for each input argument. To display data on the screen, the printf function, you will display the content of all of these variables, and inside the control string we have the formatting for each input, for each output argument here. Let's go to this example. If you want to save some time, you don't have to retype, you just copy paste. Highlight, Control C, go back to the editor, Control V is paste. Of course, you don't have to make it pretty, just leave it as it is. So now we have item is a character array, part number is integer array, part number is integer variable, and cost is a floating point variable. And we want to capture data for item, part number, and cost using the scanf function. So item is a character array, so the format is going to be S for string constant, part number D for integer constant, cost is floating point constant, so it's going to be %f. Next, we use the printf function to display on the screen the content of each of the variable. So just compile and run. So the cursor is now blinking. This is the scanf function. So I can enter item, part number, and cost in a single line. For example, red pen. I cannot use a blank space here because a blank space is end of data. Blank space, that's the end of data for item. Next, part number, integer, and cost is going to be floating point constant. So printf basically displays the data as we entered them on the keyboard. Data can be entered on the same line or on separate lines. For example, enter, because enter is also end of data. I can put the cost here and enter. So that's the end of data. Or I can enter. It's still not producing any output because it's still waiting for the last data, which is cost. Now all the data are entered and we have the printf producing this output. The printf function basically displaying the data as captured in the scanf statement. Here we have 6 decimal places because by default printf without precision, which we will see later on, is always going to be 0.6f, which is 6 decimal places. That's the default value. Here the string constant entered from the keyboard cannot contain white space or blank character. To enter white space within the string constant, there are many ways. The easiest one is to use this method. Replace s with square bracket, hat, and /n. So replace this with square bracket, hat, /n is actually the return or enter key. Now I can enter white space or blank in the data. But to terminate the data, you must hit the enter key. Remember in the square bracket the /n, so you must hit the enter key. Sorry, wrong slash. It should be this slash. So I run again. Cursor is blinking. That's scanf. Let's say just red pen. You must hit the enter key. So the next is going to be part number. For cost, I can enter on the same line. So this basically allows the string constant to be entered with blanks within the string constant. What is a fill? A fill is defined as consecutive non-white space or non-blank characters that define a data item. The maximum fill width can be specified as in the following example. So here, scanf, in the scanf segment, we have the maximum fill width, 3 here, 3 here, 3 here, for each of the integer variables a, b, and c. So this data entered from the keyboard. 1 blank, 2 blank, 3. And the scanf segment will capture A is 1, B is 2, C is 3. Even though the actual fill width is only 1. Next, we enter the data in groups of 3 digits, separated by 1 or more blanks. So in this case, the actual fill width is, for each data is 3. And the maximum fill width in the scanf segment is also 3. So there is a perfect matching. What about this one? So in this case, there is no blank spaces in between the data. Since we have maximum fill width in the scanf segment, the computer will read 1, 2, 3 as A, 4, 5, 6 as B, 7 and 9 as C. And if you printf ABC, this is what you get. A, B, and C. And finally, for this group of data, scanf will capture 1, 2, 3 as A. After 3, there is no blank. So 4 is going to be B. Because after 4 is going to be blank, so that's the end of B. So whatever comes next is going to be C. So C is going to be 5, 6, 7. In this example, we have 3 variables, I, X, and Y. So scanf I. So I can be a maximum of 3 field width, X 5 field width. Of course, C is always a single field width because C is going to be character variable and character constant is a single character. Second line, we just produce printf on the screen, the contents of each variable. Remember, scanf, in front of the variable, you must put the %. Let's say this is data entered from the keyboard. 10 blank is data, blank, and capital T. What happened is, the scanf statement, I is going to be a maximum of 3 field width, but here the actual field width is only 2. But after 10, there is a blank. So, and that's the end of the first data. So, I is going to be 10. Whatever comes next is going to be X. 5 field width, count. 1, 2, 3, 4, 5, including the decimal point. So, 256.8 is going to be X. After 8, there is no blank. So, whatever data next is going to be Y. So, 7 is going to be captured in Y. So, we printf the contents of all variables. So, we get I is 10, X 256.8, and Y is going to be character constant 7. This is character constant 7. Of course, you want to capture all the data correctly, just don't use the field width. Take out the 3, take out the 5, and it will read correctly all this data. This is going to be I, 256.875 is going to be X, capital T is going to be Y. So that's why normally, for scanf, normally it's a lot easier if you don't use the maximum field width, unless you know what's going on. So it's a lot easier to just use what we call free formats. No field width, just %D, %F, and %S. So data separation can be blanks or return key if you enter the data from the keyboard. In the printf function, we can specify the minimum field width by preceding a conversion character by an unassigned integer. D, E, F, and so on. These are the conversion characters. Where C is single character constant, D for integer constant, E for floating point constant with exponent, F floating point constant without exponent, G, if you use G, the computer will decide when to print E or F. And of course, S for string constant. So in this example, we have integer variable A with initial value, integer constant, 5-digit integer constant, 1, 2, 3, 4, 5. Of course, you can program this. Just Control C, go to the editor, Compile and run. So what happened here? In the printf statement, we specify the minimum field width. Minimum means if there is not enough field width, the computer will add so that all the digits or the number will be displayed on the screen. So here we say printf a in 3 field width, but the actual data is 5 field width. So in this case, the computer will add the 2 to this. It will change this to 5. Of course, you cannot see it here. That's why you get this output. Next, printf a in 5 field width, exact matching. The actual field width is 5. So you get this. Next, we say printf a in 8 field width. So from the left, 1, 2, 3, 4, 5, 6, 7, 8. 8 spaces, 8 slots from the left. But to printf a, you don't need all 8. Only requires 5. That's why you have 3 leading blanks. Because there are 8 field width and the data is only 5 field width. So it's going to fill right justified. So you have 3 leading blanks. Float. So here we have floating point variable x with floating point constant. When you specify the minimum field width, it's going to be automatically going to be 6 decimal places. So without decimal places, by default, it's going to be 6 decimal places. The first one, 3f, 3 field width. Because this is actually 3.6. 6 decimal places mean 0.678 with triple zeros. So it's going to be how many field width? 6, 9, 10. So it's going to be 10.6. But here, 3 field width. Not enough. The computer will change this to actually 10.6. So you get this. Next, 10 is actually 10.6. So more or less exact field width, 10. Here, the 13 is going to be 13.6. 13 field width, 13 field width with 6 decimal places. But for this data, it only requires 10.6. So you have 13 minus 10. That's why we have leading blanks of 3. Total field width is going to be 13. From here, you can count 1, 2, 3 up to here. It's 13. Notes here. Without decimal places, here is free format. Here, with minimum field width. By default, it's going to be 6 decimal places. Some notes here. For E format, printf E format, when you have floating point constant, it's positive. Free format, this is equal to 6 decimal places. The exact specification is going to be 13.6. So this is going to be precisely 13.6 for positive floating point constant. For negative floating point constant, it's going to be 14.6. 14 field width with 6 decimal places. For all floating point constant, when you use E format, first convert the number to scientific notation in this form. A times 10 to the power b, with the base or the magnitude of the base a is going to be a is greater than or equal to 1, but less than 10. In other words, a is going to be a non-zero single digit number, and b is an integer exponent. For example, here we have floating point variable x with initial value. Convert to scientific notation. So you're going to have, this is actually 3.456780 times 10 to the power 2. When we printf using this minimum field width 3, so the without decimal places is going to be 3.6. This is a positive number, so the correct spec is going to be 13.6. So in this case, it's 3.6. It's not enough field width. The computer will change this to 13. To be more precise, it's going to be 13.6. So you have exactly this output. 13 field width with 6 decimal places. And of course, for the exponent, it's always 3-digit exponent. E, the sign of the exponent, and 3-digit. Next, 13. 13 by itself is without decimal places. So the computer will change this to 13.6. Of course, 13.6 is exactly as the first one, 13.6. The last one, 16.6. But for positive numbers, require only 13.6. But the field width is still 16 here. So from here, you can count. It's going to be 16 field width, but only require 13. So this is going to be leading blanks. 16 minus 13, there will be 3 leading blanks. Next, for negative number. So here we print f. So negative number, scientific notation. And for negative number, it's going to be 16, sorry, it's going to be this one, 14.6. So 14.6 is the exact spec. Here we have 3. 3 is not without decimal places. It's going to be 3.6. But 3 is not enough. You need 13. So the computer will change this to 14.6 for negative number. So you get this output. The field width is going to be 14. You can count from here to the left. They're all 14. 14 field width. 6 decimal places. Next, 14. This is going to be 14.6. So you get this. The last one, 16.6. But requires 14 field width. So that's why you have 2 leading blanks. The field width here is 16. From here, you can count to the left, 16. For the symbol, if you use capital E, the output is going to be capital E. Small e is just the case. Here, capital. Here also, capital. Next, the maximum number of decimal places, or we call it precision, for floating point constant only can be specified as follows. Here we have floating point variable x. Printf in 7, minimum of 7 field width. So without decimal places, it's going to be 7.6. But for this number, 6 decimal places is going to be 6. This is significant number. Plus 3, 9. It's going to be plus 1, 10. So it's going to be 10.6. The computer will change this to 10.6. So that's why you get in this output, this is actually 10.6. Second line, printf 7 field width with 3 decimal places. So 3 decimal places is this number. So this is going to be 3 plus 3 plus this one, 7. This is 7.6. Sorry, 7.3. 7.3. So this is precisely 7.3. So you get left justified this output. 7.1. So 1 decimal place is going to be 123.5 because it's going to be rounding off. So 123.5 is actually 345, 5.1, 5.1. So 5 fill width, but the spec says in 7 fill width. That's why you have 2 leading blanks in front. The E format for precision. For this number, convert to scientific notation. It's going to be 1.23456 times 10 to the power 2. This is going to be positive number, so 13.6. It's actually 13.6. You get this? 13.5. You take out the 0. It's only 5 decimal places, but the full width is still 13. That's why we have one leading blank here. 13 fill width, 3 decimal places. So you take out all this, remove this, push this to the left, sorry, to push to the right, because it's going to be right justified. So you're left with 1.235, 3 decimal place, but the full width is still 13. The precision can also be specified without specifying the minimum fill width. So here we don't have the fill width, only the precision. Without the fill width, only with precision, the output are all going to be left justified. So there is no way there's going to be a leading blank. So here we have free format F. So it's going to be left justified 123.456 because this is automatically going to be 0.6F. Next, 3 decimal places, no fill width, no minimum fill width. So basically you remove this 3, you're left with 3 decimal places, 123.456. The last one, 1 decimal place. So you're left with 123.4, it's going to be rounding off, so 0.5. This is 1 decimal place. No fill width, so left justified. Okay, next. Let's say we have E format, no fill width, only the precision or the decimal places. Of course, %E is going to be, it's a positive number, it's going to be exactly 13.6E. This is what you get. Next, E format, no minimum fill width, but 5 decimal places. So you take out the 0, push to the left. This is what you get. Last one, no fill width. Remember, without fill width, they are all going to be left justified. So 3 decimal places, remove all these 3, push this to the left. You get this. Finally, flag. A flag can be added to a character group within the control string. Okay, within the control string, between these 2 single quotes. In only the, of course, printf statement. So a control string is usually made up of fill width, precision, this is precision, and conversion character. D, E, F, those are conversion characters. And the flag must be placed immediately after the % sign. There are many flags. These are the more useful ones. If you have this flag, it means data is going to be, in the printf statement, in the output, is going to be left justified, there's no leading blanks. A plus sign means a sign will always precede the data item. So number, negative or positive, you always have the sign there in front of the number. If you put 0 there, it means that if there are leading blanks, replace the blanks with 0. So in this example, we have integer variable I with integer constant of 3 fill width. 1 to 3 requires 3 fill width. It's the actual fill width. Printf, here I use the semicolon to mark the end of the full colon to mark the end of data, like here. Without this, you don't know whether the end of data is it going to be here or where. This is free. The first one is free format. Printf d. So the computer will put 3 there. There's no fill width, so the fill width is going to be the actual fill width 3. The computer will change this to 3D. You get this. Next, print this constant in 6 fill width, but the actual fill width is only 3. But you must follow. It says there in minimum of 6 fill width. So the fill width is 6. So the data is going to be right justified with 3 blanks. 6 minus 3 is 3 leading blanks. So right justified, of course, in 6 fill width. Next, we have a flag 0. It means that without flag, you have this. With this flag, it says that if there are leading blanks, replace them with zeros. That's why you have 0 in place of the blank spaces. Next one, this flag is for left justified. 6D without flag is this. Now we say left justified. That's why the output is pushed to the left. It's left justified, but the fill width is still 6. This flag is the sign flag. This is 6D with the sign. That's why we have the positive sign. This is positive number. Of course, if the number is negative, even without the flag, you still get a negative sign. Last one here, left justified and with a sign. So this left justified and we put a sign. So the sign will take 1 fill width. So this is the short form for RJ, justified, and so on. Next, we go to F format with flag. X is floating point variable with this constant. Free format. For F format, it's going to be 0.6F. So automatically it's going to be 12.54800. And that is going to be 9.6. So that's precisely, of course, this is going to be 0.6F or 9.6F. So this is what you get, free format. Now in 7 fill width, well, with only 2 decimal places. So it's going to be 12.55. It's going to be rounding off. So the fill width is going to be 7. You can count 1, 2, 3, 4, 5 fill width. So right justified. Next we have a flag. It says there, if there are leading blanks, like here, now we put leading flag here, replace blank with zeros. That's why you have zeros here. Next we have left justified. This 7.2F. Left justified, basically you have to push this to the left. But the fill width still remains all here, 7 fill width. This one, the sign flag, 7.2F, this one. Well, with the sign, so the plus sign will take 1 fill width. the last one here, left justified with sign. So basically, this with sign, left justified, you have to push this to the left. This one. But still, the field width is still 7. 1, 2, 3, 4, 5, 6, 7. Flag for E format. So we have Y. It's a floating point variable. We're using E format, convert to scientific notation. Free format E is going to be positive number. It's going to be 13.6E. 13.6E. This is what we get here. 13.6E. It's free format. Now, 16 field width, 2 decimal places. 2 decimal places is going to be 1.25. Remove this. Rounding off 1.25. So this, the field width are all 16 here. So from here you can count 1, 2, 3, 16 field width. So it's going to be right justified. This is what you get, 2 decimal places. Next, we put flag. This flag says replace zeros, blanks with zeros. This flag says left justified. So we push this to the left. Next one, with a sign. (16.2) with a sign is this one. This is 16.2, but with a sign we just put the plus sign there. The last one, left justified with a sign. This is a sign, left justified, basically you push this to the left. You get this. And finally, more or less the same as this one, except this is a number less than 1. The same process. Convert this to, because E format, convert to scientific notation. Free format is going to be exactly 13.6. Left justified. 15.1E. So basically, 1 decimal place. Remove this. You're left with 6.8 because this is a rounding off. So 6.8. But the right justified, push to the right, but the field width is going to be 15. You can count from here 1, 2, 3. It could be 15 field width, but only 1 decimal place. Here it says a flag. Replace blanks with zeros. So this one with flag, that's why you have, instead of blank you have zeros. Next, 15.1 left justified. So basically this one, push to the left. 15.1 with a sign. This one, 15.1 with a sign. In this case it's positive. The left justified with a sign. So basically this one, push to the left, you get this. Okay, thank you. In the next lecture, we go to the control statements, branching operation, and looping operation. Thank you.